For decades, there's been this fundamental trade-off in how our computers work. You could have a super fast operating system, or you could have a super secure one, but you couldn't really have both. It was always a compromise. Well, today, we're going to look at a radical new design that doesn't just bend that rule, it completely shatters it.
I mean, think about it. You get a new computer, a new phone, it's got more cores, more power, but does it always feel proportionally faster? We've kind of gotten used to this idea that performance hits a wall eventually. But what if that wall didn't have to exist? What if you could build a system where every bit of power you add gives you a real, tangible boost in speed every single time? That's the idea we're diving into.
So here's how we're going to break this down. First, we'll look at the hidden bottleneck that's slowing down pretty much every powerful computer on the planet. Then we'll check out the safer alternative and figure out why it never really caught on. And finally, we'll get to the good part, a groundbreaking blueprint that promises to deliver the best of both worlds, making an OS that's not just safer, but way, way faster. All right, let's get right into it. To really understand where we're going, we first need to understand the problem that's been hiding in plain sight for years, a fundamental issue with the design of almost every OS you've ever used.
Think of it like this. Imagine a small workshop where everybody has access to all the tools on one big shared table. For a small team, this is awesome. It's super efficient. Need a screwdriver? Just grab it. That's a monolithic kernel. And for a long, long time, especially on single-core processors, this was the fastest way to do things, no question.
But what happens when that workshop gets crowded? I mean, really crowded, with dozens of workers, or in our case, CPU cores. Suddenly, everyone's trying to grab the same hammer at the same time. It's chaos. So you make a rule. Only one person can use a tool at a time. Everyone else, you got to get in line and wait. That waiting, that line, is what we call locking in an OS, and on a modern chip, it creates a massive, massive traffic jam.
And that waiting isn't just some tiny inconvenience. Imagine losing over 6% of your entire day just standing in line. That's literally what's happening inside our computers. Billions of precious clock cycles are just evaporating while these powerful cores sit there doing nothing. This is the monolithic performance wall. The very design that made it a speed demon is now its biggest weakness.
Okay, so if that big shared workshop model is broken, what's plan B? Well, let's look at the other side of the coin, the microkernel, and let's find out why it's been the underdog for so long.
So the whole idea behind a microkernel is brilliant, right? You put every single component in its own separate locked room. The network driver can't mess with the graphics driver because it doesn't have the key. It's super secure. But for them to actually do anything useful together, they have to communicate. They have to pass notes under the door, with the kernel acting as the messenger. This whole system of passing notes, that's called inter-process communication, or IPC.
And this right here, this chart is where the dream of perfect security met a very harsh reality. In a monolithic kernel, a simple task is like a quick chat with your coworker. It takes about 24 cycles. But on a traditional microkernel, that same task was like sending a package by snail mail. We're talking thousands of cycles. This huge performance tax was so insane that for decades, most people wrote off microkernels as a noble but completely impractical idea.
So we're stuck, right? A fast but flawed system or a safe but slow one. It seems like we have to choose. But what if we didn't? What if we could take the biggest weaknesses of both models and flip them into a new kind of strength? That's exactly what this next-generation blueprint is all about.
This whole new approach is built on 4 really revolutionary ideas. Instead of forcing everyone to fight over the same tools, we're going to give everyone their own private set. And instead of paying that massive performance tax for security, we're going to use some new hardware magic to make it almost free. Let's see how these pieces come together to create something, well, something pretty extraordinary.
Okay, the first step in this revolution is also the boldest one. We're going to tear down the walls we've always used for security and memory, and then we're going to rebuild them in a totally new way. Now, I know what you're thinking. Hold on. Didn't you just say putting everything in one big space was the problem? And yeah, in a way, you're right. By putting everything in one huge address space, we get rid of that super slow process of switching memory maps all the time. But here's the brilliant part. We're going to get security without the walls. So how do you stay safe with no walls? You use something called capabilities. Imagine that every chunk of memory has its own unique digital lock. A program can only touch that memory if it holds the one and only unforgeable key for that lock. And new hardware can check this key instantly. It's not an extra step, it's just part of how the chip works. All of a sudden, security isn't a performance penalty anymore, it's just physics.
And this simple idea has these huge ripple effects. Like, when your computer gets data from the network, it no longer has to waste time making a copy of it for your app. No, instead, the driver just lends the application the key to the original data. The app uses it, gives the key back, and that's it. No wasted time, no copying. It is just pure, elegant efficiency.
Okay, so we've cracked the code on having security without the slowdown. Now we can finally go back and fix that multi-core traffic jam we talked about. And the solution is to stop thinking about a multi-core chip as one computer and start seeing it for what it actually is, a tiny, high-speed network.
And this, right here, is the big aha moment of the whole design. It's called the multi-kernel model. We literally treat each core on the chip as its own little independent computer. They don't share memory, they don't share data structures. If they need to work together, they send each other explicit messages, just like servers in a Google data center.
And the results? They're a total game changer. Those traffic jams from cores waiting in line? Gone. The endless, time-wasting process of fetching data back and forth? A thing of the past. Suddenly, you have a system that doesn't just get a little faster when you add cores, it scales almost perfectly. More cores no longer means more problems, it just means more raw power for the whole network.
So, we've laid out this blueprint for a system that's secure and perfectly scalable. But the biggest question is still on the table. Is it actually faster? Let's look at the numbers and see how this new design really stacks up.
Okay, remember this number, 24 cycles. For years, this was the speed of light inside an operating system. This was the gold standard, the record that everyone was trying to beat.
Now look at this. Thanks to these new hardware tricks, a fully secure message between two isolated parts of the system takes just 109 cycles. We're not talking about thousands anymore. We are in the same league as the monolithic kernel, and we're just getting warmed up.
Because here's where the real magic kicks in. When you combine that incredible communication speed with the multi-core network design, the gains just become exponential. For apps that do a lot of communicating, this new microkernel isn't just a bit faster. It can be over 13 times faster. It doesn't just beat the old monolithic kernel at scale, it completely leaves it in the dust.
You know, for decades, we all bought into this idea that microkernels had to pay a performance tax for being so secure. But this new way of thinking totally flips that on its head. It doesn't pay a tax, it collects a dividend from the way modern hardware is actually built. Isolation isn't a weakness anymore. It's a superpower.
And that really leaves us on the edge of a totally new era. When you don't have to choose between speed and safety anymore, what becomes possible? This isn't just about building a better operating system. It's about unlocking a whole new generation of software, apps that are more resilient, more powerful, and maybe even more intelligent than anything we've seen before. The future of speed is here, and it's looking brighter than we ever imagined.